Hello and welcome to another edition of Data Center Insights by Intel. Before we begin, I would like to point out several features of the BrightTalk tool that may improve your experience. For our live audience, there's a questions tab at the bottom of your viewer. I encourage you to please ask questions at any time. Our presenter will answer them at the end of the webinar. And if we don't get a chance to answer your question, you can always tweet us questions at Intel IT Center or at @KyleAmbert. At the end of the presentation, please take the time to provide feedback using the ratings tab. We value your thoughts and will use the information to improve our webinars. Today's webinar episode is entitled An Introduction to Deep Learning and Nirvana Neon. And it is my pleasure to present Kyle Ambert, PhD, Senior Deep Learning Data Scientist at Intel Nirvana. Today we'll be learning about the Intel Nirvana Neon, a reference deep learning framework targeting ease of use, extensibility, and optimal performance on all hardware. It is truly wonderful to have all of you here today. And with that, I'm going to hand it over to our presenter. Dr. Ambert, take it away.
Thank you. It's a pleasure to be speaking with you all today. I just want to reiterate, if any of you have a question during my talk, feel free to go ahead and type it out and send it my way. Otherwise, the only feedback I really get is just my dog looking at me quizzically while I'm apparently talking to nobody. All right, let's get started. I thought I'd start a little by telling you a little bit about myself. I got my PhD about 5 years ago at Oregon Health and Science University studying the applications of machine learning to the neurosciences. Second. Okay. But actually, when I first started in grad school, I was studying the neural mechanisms of decision-making and addiction using like operant conditioning and that sort of thing. But eventually found out that I'm actually allergic to rats, which led me to more computational studies, and ultimately where I am now. A lot of my research actually centers around using machine learning and deep learning to leverage, or to extract information from unstructured data sets, something like textual data from biomedical publications, things like that. So along with pursuing that line of research at Intel, I'm also a part of the Nirvana team where we build deep learning tools for people like yourselves to use. My team actually is, we're the solutions group, so we interact with customers and help them arrive at well-defined experimental questions that they can answer with the data sets that they have. And together we create production deep learning solutions across multiple domains. My particular vertical is the health and life sciences, and we do our best to advance the field of applied analytics and optimization. So one of the questions I always get when I'm giving talks is, what is Intel doing in the analytics space? When people think of Intel, they usually think of like hardware and chips or Moore's law or things like that. And that's, right, I suppose, but we actually have a pretty broad interest in doing analytics as well. Our overall mission as a company is to provide the infrastructure that will yield the fastest time to insight. And in part that is hardware, but it also takes place in software and in the analytics tools that we can give to people. Our thought is that if we can create tools that will enable scientists and just people in general to think about their research rather than the process by which they're doing the research, and to actually enable them to do it much faster, then that will create a larger demand for our hardware. We would ultimately want to enable them to ask bigger questions of their data. And yes, great solutions require great hardware. So real quick, this is sort of a bird's eye view of what we do at Intel. We have best-in-class hardware portfolio for machine and deep learning, but obviously software is a critical part of that. You may, if you've been involved in deep learning or machine learning at all, I'm sure you recognize some of the logos here. This TensorFlow is a popular open source deep learning tool from Google. Caffe is another popular tool that's oftentimes used for image classification. But importantly, at the lowest level, we have Intel optimized primitive functions, things like MapKernel library, which is a set of tools for doing matrix multiplication, and a lot of the lower level mathematics that you need to be very fast at when you're doing deep learning, or the data analytics acceleration library, which has optimized classifiers or something like support vector machines or anything along those lines. One of the tools that we'll be talking about a little bit today is in the left side of the frameworks layer there, the Nirvana Neon. That's our that's our answer to deep learning frameworks. And so I'll give you a little bit of an intro to that today. So here's an outline of what I thought I would talk about today, barring any questions that take us elsewhere. First, I'll give you a brief overview of sort of my view of machine learning and data science. I'm a data scientist, by which I mean, I actually work on problems for customers and in the real world. Then we'll do a brief introduction to deep learning. I'll tell you a little bit about our company, Intel Nervana. And then finally, I'll give you a brief introduction to our intuitive deep learning framework, which we call NEON. So let's get started with machine learning and data science. So one of the other more common questions that I get is, and perhaps you yourself have been asked this or wondered, what is the difference between artificial intelligence, machine learning, and deep learning? This is a pretty common question to ask. From the perspective of myself, I don't think there really is a great deal of difference. A lot of it's just semantics or just the type of person you're talking to. In the 70s or the 60s, it was called artificial intelligence. Now we call it machine learning, or if you're talking to a mathematician, they may call it statistical learning theory or something like that. But this diagram actually, if you're going to try to wrap your head around the distinction between these terms, this is a good way of thinking about it. So artificial intelligence, we could say, is any program that can sense, reason, act, or adapt. A subset of those programs we would call machine learning, which are algorithms whose performance improves as it is exposed to more data over time. And then a subset of machine learning is then deep learning, which is multi-layered neural networks that can learn from large amounts of data. So importantly, deep learning is really just one area of machine learning. So just to level set on some terms here, this is how I think about machine learning and deep learning. So machine learning, when I say machine learning, I'm referring to the development and application of algorithms that can learn from data in an automated, semi-automated, or supervised setting. And subsets of this would be something like statistical learning, which would include any number of algorithms that you've probably heard about: naive Bayes, support vector machine, generalized linear model, k-nearest neighbors. Or conversely, we have deep learning, which are algorithms where multiple layers of neurons learn successively complex representations of input data. So this could include something like any number of architectures that you may have encountered: convolutional neural networks, long short-term memory for dealing with text or something like that. A couple more terms. When I refer to training, I'm talking about building a mathematical model based on some input data. And when I refer to classification, which is also sometimes called scoring or also sometimes called inference, that refers to using a trained model to make predictions about new data. So hopefully that all is review for everybody. So another important aspect of data science work is really this workflow you can see here at the bottom of the chart. So when I'm talking about data science, what data scientists spend a lot of their time thinking about is really this workflow here. It's the mechanisms by which we can acquire, ingest, and clean data. It's methods for storing and managing those data in a persistent way, like a database. It's methods for feature engineering or feature extraction. Then actual analyses, like performing exploratory data analysis, making sure that the assumptions of the model you're creating are met in the data set. And then finally, model building. So this would be the act of like training a support vector machine or a neural network of some kind. And then if you're in a production environment, that would then be, you deploy that model into production and then observe it over time to detect something like concept drift or something like that. And if you've worked in the field of data science for very long, you know that this is actually kind of an idealized view of the workflow. It's really a little bit more like this. So you get your data from the customer and they forgot to put the header row on it, or they maybe labeled it incorrectly, or the only documentation they gave you is just the name of the file, which is dataset1 rev2b or something like that. So you have to email them and get better documentation. Then you have to clean the data. You realize that maybe they sent you the wrong data set. Main point here is that data science is very much iterative. and it's a messy, messy endeavor to engage in. And so because of that, it becomes very important that we think about, that we have a good understanding of the types of tools that we're using and how we can move from one portion of our workflow to the next. Just going back here, when we're working in something like support vector machines or like training a random forest, it's maybe a bit easy to conceptualize the handoff between acquiring our data and persisting to the data and extracting the features. This is actually much more difficult when we get into the realm of deep learning. The workflow still applies, but the way we think about or how we actually go about doing elements of this workflow do change slightly. All right, so let's talk a little bit about deep learning. So I like to provide historical context for things when I'm giving presentations, because I think it's much more interesting, and it provides context for how we can study the questions that have already been asked, or why we might want to revisit certain questions. So I think you could reasonably trace the origins of deep learning all the way back to 1949, when Hebb published a book you may have heard of called The Organization of Behavior. This has really documented a lot of the neuroscience findings that inspired some of the computational neuroscience tools that we've adapted in deep learning. So in the 60s, neural networks were used for binary classification to some degree of success, but popularity quickly dried out in the 70s after they were perhaps overhyped in the 60s. And then there were some proofs that came out from a guy named Minsky in the 70s that kind of showed that maybe it wasn't all that we really wanted it to be. Importantly, a large part of the dry-up was that there was not really a good way for training large networks reliably, in part because of the hardware that was available, but also because we just didn't have the algorithmic tools yet. So in the 80s, we started to use a method that we'll talk a little bit about today called backpropagation, which we use to train deep networks of multiple layers. And then in the 90s, a guy you may have heard of named Vladimir Vapnik created the support vector machines to a great deal of success. And that kind of stole the renewed thunder from the neural networks a bit. Because these had a lot of, he was able to show they had some nice theoretical properties and was able to provide guarantees on the bounds and things like that. So what brought us back to deep learning and deep neural networks was in the 2010s, access to large data sets, more computation power allowed us to get state-of-the-art results in very complicated tasks that are difficult to adapt into a traditional machine learning paradigm like speech and vision and natural language processing. So today, deep learning is actually a fast-moving area in academic and applied analytics, and there are many, many opportunities for new discoveries. So let's talk a little bit about the practical differences between machine learning and deep learning. So here you can see a picture of my dog Harrison on her birthday. And let's say we wanted to build a classifier that could look at images and say, is this an image of Harrison, or is it an image of another dog or something else? So what we might do in a traditional machine learning context, advance the slides here, we might say, okay, as an expert on Harrison-ness, I know that maybe the distance between her eyes or the length of her snout or the angle at which she opens her mouth is a good, reliable measure of whether a dog or an image contains Harrison. So we would figure out a way to encode that in the computationally accessible format. And then we would hand it off to whatever our favorite algorithm is. So support vector machines for most of my career because I work in text, or random forest more recently. And so then, we would create this pipeline and then get an answer if, yes, this dog is Harrison. So really want to point out here, in traditional machine learning, what we're doing is imposing our domain expertise on the algorithm and saying, I know as the expert the best way to determine Harrison, and we're going to encode that in a computationally accessible way and then train our algorithm. So deep learning is slightly different. So if we wanted to build an end-to-end pipeline for deep learning, for a deep learning approach to determining whether an image contained Harrison, what we'd actually do, in contrast to the traditional approach, we would build an architecture, much like the one pictured here, that would enable the machine to discover the best features on its own. And then it would we would train this model, giving it multiple images to look at, and then it would determine on its own whether the image contains Harrison. So this is an interesting conceptual shift that I really want to emphasize. Rather than imposing our view of the domain as the expert on the machine learning algorithm, what we're doing is creating an architecture for our network that will enable it to extract the best features that lead to the best performance on its own. So we're letting it discover, or as a data scientist, what we're doing is creating that architecture in a way that best enabled it to make those discoveries. So importantly, even though this is a pretty big conceptual shift, the same rules still apply for deep learning. We still, just advance the slide here, we still have to do pre-processing for our data. We still have to do feature extraction. It's just that we're going about that in a different way. We're creating the model architecture rather than performing the feature extraction on our own as data scientists. And we still need to think about parsimony and model selection. So, for example, if I have a deep neural network that has 60 million parameters or something like that, I need to be able to justify that increased number of parameters using improved model fit. So I might use AUC or some area under the curve as my metric for quantifying model performance. So I would need to actually quantify that trade-off is justified. So, I mean, even though we still have to do all these things, again, the way we go about doing some of this does change. And there's also some data considerations that we need to think about. Keep missing the forward button here. Okay. In particular, there's some considerations we need to think about with regard to our data. So for building a good image classifier for identifying Harrison in photos, we'll need to find multiple photos of Harrison, so you can see a few additional ones here. And preferably these would have different characteristics. We'd want to expose our classifier to different lighting or other aspects of Harrison obscured, like might cover up her eyes with a hat, so the machine learns how to identify Harrison outside of just looking at her eyes. Additionally, we'd also want to find images of puppies that aren't Harrison, so that we can be sure we're not just building a puppy classifier or something like that. And finally, if we're going to be using our classifier on images an image data set that contains things that aren't puppies at all, we would want to include things that are clearly not Harrison, like maybe our president or a bird or a castle. So importantly, not advancing, just a second. I think we may have frozen the slides here. Hold on one second. Apologize for the delay. Hey, Louis, are you on? Can you unfreeze this? I think it's frozen.
Dr. Amber, I think I can start forwarding the slides through with you if you'd like.
Oh, yeah, sure. If you could click through. Is it frozen for you as well?
No, I think we're looking at slide 44 right now. Maybe just give your browser a quick refresh and we can continue on.
Okay. Apologize for the delay. Just 1 second. I seem to have perhaps lost internet for some reason.
So Dr. Amber, one option is that you can just talk to your slides on your computer if you have them open, and I can just flip through them as we go.
Okay, let me pull them up. Okay. So can you describe to me which slide you're on so I can...
Yeah, we're on slide number 44. We just learned that more data is always better.
Oh, good.
Okay. Yeah.
So yeah, then we kind of skipped a few important key points here. So I'm going to guess that the whole slide here, which on my version is actually 23, is built out. So there's a few things that we need to think about differently when we're building our deep learning classifier. We need to expose it to pictures of our dogs or not dogs using after applying various transformations. So we might rotate the image in different ways. We might obscure parts of the image. Importantly, we would need to make sure all images are the same size. Usually this is part of our pre-processing for our deep learning model. So we would go through and reshape the images if we needed to, and that's all fine. Also, I think I skipped this. We want to make sure there are expert-assigned labels. This is very important. This is a supervised learning approach to image classification, so we don't want to go through and label all those, because that's what we're going to leverage to determine how good our model is. And of course, more data is always better. If a client asks me how much data they need to give me, I just tell them more until they stop asking or something like that. For an image classifier, it really depends on, in part, the complexity of the domain that you're working in. But as a general rule, more is always going to be better, particularly more labeled data. In part because with an image classification model that potentially has millions of parameters, we need to give it enough data to fit all of those parameters. So next slide. Networks of artificial neurons slide, hopefully. So let's look at the building blocks of deep learning networks. Here you have the artificial neuron, which performs a local operation on its inputs. A good starting point is to think of deep learning models as containing three types of neurons: an input neuron, a output neuron, and a hidden neuron. So when I say hidden neuron, that's just a neuron that's only connected within the network itself. So it's not receiving input from our data, and it's not outputting anything to the user. So these neurons are interconnected, and the magnitude of the connections, or the strength of those connections, is something that we're going to be estimating. These values are referred to as weights. So each neuron takes a set of inputs x and returns a scalar output y by performing an operation that you see here. So units x are multiplied by a set of weights, and then a baseline offset is added. And the results pass through what we call an activation function, next slide, which yields the output for unit yi. So you can see here a couple examples of activation functions. And there's just a set of activation functions that are typically used. But one thing they share in common is bounding the values between certain a floor and a ceiling. And this is a consequence of the way that we actually estimate the collection of weights. We don't want those values to explode up to infinity or diminish down to zero, in which case we would be doing no learning at all. So here's a couple of them. The tanh function takes an input from a domain negative infinity to infinity and then squashes it within a limited range of -1 and 1. Next slide. Actually, just 2 slides. So you can string these together in a network like the one you see here. Is just a simple multi-layer perceptron type network here with input and hidden and output layers. So this is just 3 layers, but they can get obviously much more complicated. This one here is just a feed-forward network, meaning that everything's just moving from input to output. So from a practical perspective, there's a lot going on here for a data scientist. We're keeping track of potentially many parameters and a large data set. So we just want to emphasize the explosion of moving parts. We really need to be able to understand and keep track of what sort of model is being built. And this becomes even more important in this domain. So next slide, let's work through a practical example. If any of you have heard of, a common task in deep learning is recognizing handwritten digits. So we use a common open source data set called MNIST. Next slide. So MNIST contains 70,000 28 by 28 pixel images, and the goal of our network is just going to be to classify the images into a digit from 0 to none. So next 2 slides. So let's take a look at what a simple network might look like here. So a 28 by 28 pixel image is going to have roughly 784 pixels. So we're going to need an input neuron for, or an input unit, as we could also call them, for each of the pixels in that 2 by 2 space. So that first layer is going to have 784 input units. Then we might want to do a fully connected hidden layer. We call this an affine layer. So we would have potentially maybe 100 hidden units. So you can pick as many as you want, doing experiments on your data set to find the best combination. So if we had 100 hidden units, then 100 times 784 would give us about roughly 78,000 connections. And then if we had an affine layer connected to output, so here we know our output is going to just be the numbers 0 to 9. So that again is just 100 times 10. So in total, that's going to give us about 76,000 parameters for our model. And this is just a relatively simple model. Next slide. So for the output, each unit in that output layer is going to encode the probability of the input being the digit I. So this is actually going to sort of be a distribution over the possible outputs. So on the next slide, we're going to take a look at the procedure for training, which contains, next slide. First step, we would randomly seed our weights. To start this whole process, we need a best guess as to what the weight connection values are going to be. And if outside of domain knowledge, you would just pick a random values. So next slide, we would do a forward pass. Next, we would then evaluate the divergence of our model's accuracy using some cost function. Next slide, we would then backward pass or back propagate that delta back through the network. And then next slide, we would update the weights. So let's look a little more closely at at these steps. So start with the next slide, forward pass. If you can advance it 4 steps, that would be easy. That should be complete build for this. So we already talked about randomly seeding the weights. It's standard practice to just use maybe a normal distribution to assign those values. It doesn't really matter. We're just going to start somewhere, and it's going to be really bad at first. So we, could potentially, train this model using a single image. We would pass it through using a forward pass, and then you can see here the output that it would calculate here. You can see this vector sums to 1, and it's not particularly good. 0 index, so the true value of 3 is only getting a 0.3. So this right now is guessing it's an 8, which I guess isn't totally unreasonable. But importantly, we would then calculate some cost function, and then here on the next slide, sorry, we have our ground truth. We're going to use that relative to the output vector and compute some cost. Next slide. So then we backpropagate that information through our network. Next slide again. So I won't get too much into the calculus of how this actually works, but I encourage you to study it because it's very important. Basically, we're going to backpropagate that and then compute some delta W, delta weight, to then update our weights. So you can see here from hidden to output, we're updating that with delta W J to K, and then for the input, we're delta W I to J. And in a very high level, the next slide, next 2 slides. So it should be backpropagation, and then we have C, Y, comma, true. So basically what makes this possible is the chain rule in calculus. We have these simple activation functions, and we can chain those together to then compute the updates to our weights. Next slide. Okay, so let's talk a little bit about the practical considerations in training. So if you have a single image that you're training one at a time, we could then pass that image through, you could do the forward propagation, cost, back propagation, then compute delta W. We could do this for each image in turn over the 70,000 and compute delta W at each time. But what you'd find is that is not particularly computationally efficient, sorry, next slide should say gradient descent in the orange box around the whole thing. We then updates our weights using this calculation here, delta W equals alpha times 1 over n, and the sum of the delta W's. So this would just be the gradient descent approach. The next slide. So what we actually do in practice is called stochastic gradient descent, or what we call it in my lab, mini batch gradient descent. And this is usually what people actually do. So they'll randomly collect a group of images and then pass them through the network as a group or one at a time, and then compute the updates at the end. And then we would do that for our next mini batch. So on the next slide, you can see, next slide again. So a complete pass-through of our entire data set, however many mini batches that might be, in the field, we call that an epoch. So the first epoch, epoch 0. The next slide, we have our epoch 1. And if you could forward 2 more slides here, we have some sample numbers. So you can see here, AlexNet is a commonly used image classifier algorithm. You can see as we proceed through in time, as epoch numbers increase, the top, our test error metric actually decreases. And this is a good thing. That's what we want to see. So next slide, please. So if you're like me when I first started in machine learning, you're probably asking yourself, why does this work at all? And that's a really good question. I guess the short answer would be, I don't know, or I could just say math. Academically, we say this is still an active area of research, which sounds a bit more intelligent. And that's true. It is a bit confusing, but we do have some good ideas as to why this works. So we've always known that the way data is represented is critical to guiding learning. And in deep neural networks, each layer's representation is expressed as a function of the previous layer, which is to say we are learning a hierarchy of representations. And this nicely reflects the structure of the natural world. Low-level patterns like curves and whatnot form higher-level features like a smiling puppy dog, or angle might be the hat that she's wearing. And in fact, this is very similar to the way the human brain's visual system works. By encoding organizational structure of the natural world in our model architecture, we more easily lead the model to find the right features. You could also think of neural networks as just a computer program with each layer representing a step of computation. And then given enough data, the model is not just recognizing the patterns in the input, but learning a set of computations to operate on the input, which has much higher expressive power. So next slide. So yeah, a little bit about our group, Nirvana. Next slide. Here is Nirvana in 30 seconds, or possibly, hopefully less. Our deep learning platform is at Nirvana is full stack. That is to say, it goes all the way from the hardware up to the software solution. So this makes it easy to ingest and augment your data, train your data, and ultimately deploy your models. So today, our stack consists of 3 main components. First, a custom neural network processor chip that accelerates deep learning, which is in production. And 2, our deep learning framework, which we call Neon. And then 3, our cloud platform, which enables customers or researchers to perform scalable training and deploy models into production. So this means you don't have to necessarily go out and buy a huge computing platform. You could just use our own. So I'm going to walk through, won't spend too much time on the hardware or the cloud solution, but we will talk about the Neon framework. Sorry, if you could advance 3 slides, should be complete build. So you can see here, Nirvana Cloud at the top, our deep learning framework, which provides some acceleration on many important tasks in deep learning. Next slide. So let's talk a little bit about Neon. It's our open source deep learning framework, and it has an intuitive Python API, which as a data scientist, I think is a really good thing. And it really makes the sort of complications that underlie model experimentation and creating a custom architecture much easier. So let's talk a little bit about Neon. Sorry, next slide. Okay, next slide again. If you have access to these slides after my presentation, this is a great recipe to follow. First, you can just clone Neon off of our GitHub repo, and then install some dependencies which change depending on whether you're using it in Python 2 or Python 3. So hopefully the syntax makes sense. Just pip install those, virtual environment, etc. If you're on Macintosh and you have the advantage of using Homebrew, the package manager, to install a variety of packages, you could install OpenCV or OpenCV3 if you're going to be working in computing vision. Then make it, and then it comes with, we recommend deploying it within a virtual environment. So you just, in line 5, activate the virtual environment, and then you can run the MNIST multi-layer perceptron model that we just walked through. And then if you want to exit the virtual environment, you just type deactivate. Next slide. If you want to look at the documentation, which I highly recommend, you could follow this URL shortened here. Okay, next slide. So the way that we set up Neon is really to, the idea is to mimic the actual ingredients of deep learning, which from my perspective are here. There's 5 main components: your data set, your model or your layers, the architecture that you're defining, the activation functions therein, the cost function that you're using, and then the method of optimizing your weight parameters. Next slide. Here's a high-level overview of the way the library is set up. So starting at the top, it works on any backend. Right now we are in the process of building our own custom hardware, but the idea is that whether you're running on GPU, CPU, whatever, or our own custom hardware, Neon will work the same, and it will work very fast. And you don't have to change your code when you're moving from one environment to the next, which is great. Comes with a variety of data sets that you can use for training your model architectures. So MNIST here you see, which we already talked about, a variety of image data sets like ImageNet 1K or 1000. Variety of initializers. This is where how we're initializing the weights for a model that we're training from the ground up. So we talked about Gaussian model training, but there are other distributions that you might be interested in using. Optimizers, activation functions we talked a little bit about. Here you can see a handful. I think there may be more now. Rectified linear is a very common one, or ReLU as it's sometimes abbreviated in literature. And then layers, these are the components that you'll use to build a custom solution. So like convolution layer we would use in image classification, pooling, deconvolution, etc. There's a variety of cost metrics you can use as well for classification, image classification type of paradigm. Cross entropy is really prominent, so you'd oftentimes use that. And then finally, some metrics for evaluating the accuracy or the goodness fit of our model, like misclassification for the top 1 or 5, accuracy, precision recall, etc. Next slide. So something that comes along with the Neon installation is a variety of curated models. And here you can see a common curated model used for image segmentation. So this is sort of pixel at the pixel level performing classification, like for what constitutes a continuous image. So you can see here we're classifying where the road is or where cars are. And so this is really sort of gets at the operating model of how we work as a team at Nirvana. We find an interesting model in the academic literature and then find a customer that is interested in solving some problem, and then we adapt that model from the academic literature and then give it to them or put it on our model zoo curated model library on the next slide. So you can see here a variety of models that are commonly used in the literature. GoogleNet is a very complex approach to image classification that works quite well. AlexNet is also a very successful approach to image classification that is slightly less complex. The idea here is that you don't always have to start from scratch. Let's say I really was building a puppy classifier for my dog Harrison. I could potentially take I could download the pre-trained weights from AlexNet that we have stored on our curated model library, and then just slice off the last layer, which is maybe performing a 1,000-weight classification for the ImageNet task, and just change it to performing binary classification, as in Harrison, not Harrison. So I would need to, in part update some of those model weights, but I'm not necessarily starting from random. I'm starting from a pre-trained collection of model weights and then adapting it from there to the best fit. Next slide. Next slide again. So let's talk a little bit about loading data in Neon. There's a couple of ways of doing this. When your data is small enough to fit into memory, it can be directly loaded into NumPy arrays, which we then translate into our own internal representation, which we call array iterator objects. Next slide. So one thing that's important to think about here, when we have a JPEG or like a picture of my dog or something like that, that's not what we're actually giving to the image classifier. It wouldn't necessarily know how to handle that. It's important we're actually making it in some sort of computationally accessible format. So in this ingestion step, we're translating it into some numerical representation or matrix representation or tensor representation, and then putting it into a NumPy array at that point. Next slide. So here you can see we're loading a data set and using our convenience function, image loader, pointing it at the data, telling it some of the dimensionality, and then naming it. This might be our training data set. Next slide. And you can think of analogous sort of approaches for data that's in different modalities. So in speech, for example, we need to translate the waveform of audio into some sort of computationally meaningful format. For text, it's a little easier to think about, at least for me, probably because that's my area. But you're not just handing the classifier a PDF or a textbook or something. We actually have to extract out the text and figure out if we want to have unigram or individual word representation or bigram, which is just consecutive words or something like that. Okay, next slide. So a little bit more about the Neon workflow. Here you can see the sort of 6-stage workflow. And we'll go through this in a couple of different ways. So next slide. So this is kind of a nice representation about how a very, very simple multi-layer perceptron that we talked about, how you might write that out. So we, in the kind of pinkish square here, we're loading our data, then we're defining our model, then defining our cost function, our optimizer, finally our callbacks, which are tasks the library is going to be performing while training a model. So we may want to generate a graph like we looked at earlier for the AlexNet accuracy over epochs. So to generate a graph like that, we would leverage callbacks to get those data. Next slide. So let's walk through what this looks like in Python code, which is probably the thing that most of you are familiar with. Next slide. Next slide again. Okay, so this is an actual, very short, very simple deep neural network script in Neon. So you can see at the top, we're loading the Neon library just like we would any other Python library. Okay, so we generate the backend here. This is actually, you can either generate it explicitly or it will be done sort of behind the scenes when you parse your arguments. So it may be defined in your command line, or it will just use a default. Next slide, we load the data. So here we have a convenience function for loading the MNIST data set. So we can either provide it a path to the data directory, or I believe it will default, if there's no argument given, it will just download it from, I think, Jan LeCun's website. So then we want to partition into a training set and a validation set, which we'll use to train and then make sure it's important to have a holdout data set that you can evaluate your model to determine the extent to which it is generalizable outside of the data that it saw in the training data set. Next slide. So then we want to specify our model architecture. So you can see here we're initializing our weights with a Gaussian distribution, then defining the layers in our model architecture, and as well as defining the cost function, which here we're using binary cross entropy. Next slide. So the model architecture is really the interesting part. So kind of called out specifically for our simple multi-layer perceptron model that we've talked about a couple of times already. This is what that would look like. If you're building long short-term memory or LSTM type model, which you may have heard about, this can be used frequently in text analysis. This is how you do that in Neon for a very simple architecture again. And next slide. And then finally here, if you're building a convolutional neural network based on the AlexNet architecture, this is how you would do that in Neon. Okay, next slide. So it should say defining training parameters. So for defining training parameters, we define our optimizer here. The next slide again. We then finally train our model. So here we're just calling MLP is the variable holding our model object, and we just call its method fit. So importantly, everything up to this point hasn't actually executed much. We use lazy evaluations. So until we call fit, it's just kind of it's defining some methods that it's going to follow. We're not actually running anything until we call fit, which makes debugging your code potentially much faster. And then next slide, we finally evaluate it. Here we're defining an error rate based off of misclassification, which we then give back to the user by writing it to the log. Next slide. And I talked a little bit about callbacks. So here you can see we've maybe defined customizable callbacks here. I think this may even be the default callback. It's going to give us information about the cost at each epoch that we're using during training. And then finally, misclassification error there at the bottom. Okay, next slide. Okay, so we're out of time. Next slide again. I just want to summarize here. Deep learning methods are powerful and versatile. Next slide. And it's important to understand how deep learning relates to traditional machine learning methods that you probably already work in. The rules and the math and the statistics, all of those still apply. And so don't think you have to start completely over. Any knowledge that you have from traditional statistical learning theory still applies here and will actually, translate just as well. You just need to think about how the workflow has changed slightly or how it actually carries out those operations. Next slide. And finally, the barrier to entry to using deep learning in practice, in my view, is lowered quite a bit with the Neon framework on the Nirvana ecosystem. Next slide. So if you want to get in contact with me, send me an email or ask a question, feel free to email me at kyle.h.ambert@intel.com. Or if you like, send me a question or follow me on Twitter if you like crazy machine learning jokes or something at the Kyle Ambert. Next slide. And with that, I'll take any questions you guys might have.
Yeah, Dr. Ambert, so it looks like we have several questions that came in from the audience.
Great.
The first question, is what sorts of deep learning research questions is Nirvana currently pursuing? Yeah,
that's a great question because we're in some ways we think of ourselves first as a research organization as well as one that serves our customers. So one of the really interesting things that we're working on right now is different representations or different ways of representing weights during the training phase of stochastic gradient descent. So these would be like low low precision representations, and this is an active area of research as well. For myself, I work frequently in the health and life sciences vertical, so I'm looking at different applications for deep learning that haven't been identified in the health and life sciences, which, if that's your area of interest, it's still very much early days in healthcare for how to leverage deep learning in a way that both integrates into traditional physician workflow and also doesn't violate healthcare privacy concerns. So that's also a really interesting and active area of research right now.
Excellent. So another viewer asked, there are many open source deep learning frameworks to choose from. How should I decide between them?
Yeah, that's another great question. I think it in part depends on the area that you're working in. So you might look at what other people in your field are using, because that's probably going to give you the most use for the amount of effort that you're putting in. So in academia, that might use something like PyTorch, or TensorFlow is definitely the most commonly used one right now. But if you're doing like image classification, Caffe is always a good place to start as well. I like Neon a lot because I've been a Python programmer for 15 years or so, and I think the Python API is really, really nice, and is kind of a nice way to get introduced to and think about the different elements of a deep learning workflow.
Excellent. So another viewer asked, I'm starting a new image classification project. How do I decide what model architecture to use?
Yeah, that's a great question. So I think it's probably good to start with some of the model architectures that already exist. You may not need something as complex as GoogleNet. You could use an AlexNet type of architecture. If you want to build your own custom architecture, it's pretty standard practice to use convolutional neural networks for image classification. So you'd want to read up on that so you can kind of on your own make an intelligent choice on how to differentiate between the different approaches. Yeah, I think that's where I would start.
Excellent. And then another user asked, how do I decide between a deep learning and classical machine learning approach for a data science problem?
Yeah, I would just recommend thinking about what we talked about at the beginning, sort of the slight shift in thinking from telling a machine what the best way to encode features is versus an architecture that will enable it to find that on its own. That would be one. Two, if you have a lot of data and you're working in a sort of data modality that isn't commonly used for traditional machine learning, deep learning might be a good place to go. Something like text analytics, although does have a pretty rich history for traditional machine learning, but some of the actual applications that are being enabled by deep learning, I think, would be difficult to do using, say, a support vector machine or something like that.
Excellent. And then the last question that came in, a user asked, how should I optimize my batch size for training?
Oh, yeah, that is active and a very active area of research right now, actually, and one that we're interested in at Intel Nervana as well. So as a general rule, the bigger the batch size that you use, the more likely you are to run into issues with the gradient descent. So by issues, I mean it may not generalize as well, but it's difficult without kind of drawing a whiteboard. But you can kind of think when you're fitting a model, you're looking for the minima of the cost function that you're trying to you're sort of traversing over this graph and looking for the optimal fit. And with a large batch size, there's some evidence showing that you're going to find kind of just a very sharp minima. But what you actually want to do is try to look for a broad, flat minima. The idea is that you're only looking at a random sampling of the population that you're actually trying to classify on. And if you fit your model to a point where there's sort of a range of good fits, that's probably going to be the best thing to do. I will say, though, that there's an interesting paper that came out today from a Facebook research team in which they kind of throw this sort of rule of thumb that's been pretty common in the field on its head, and they've trained, I think, using 8,000 batch size or something like that on a very powerful computing system. And they kind of talk about how the trade-off between batch size and learning rate, which we didn't talk a lot about, and how to optimize learning rate if you do want to use batch size. So it's very much still an active area of research, but there are some sort of general rules of thumb.
Excellent. Well, that's all the time we have for today's presentation. I'd like to say a special thanks to Dr. Ambert. We really appreciate you taking the time from your busy schedule to talk with us today. And to all of our audience members, we hope you've enjoyed today's webinar, and we look forward to joining you in the future. And thank you, and have a great day.